I have a few slides to share, and as I mentioned, I will do a subset of what things are touched upon. Many of you guys are working in the real agricultural field. Unlike me, I am more kind of close world and sort of look at more theoretical aspects of soil moisture and soil physics. But so what I'm going to do is kind of mix and match with some of my experiences, and so hope that I will give you an introduction about soil moisture. So let me get into my slides. This particular preparation helped me to dig deeper into soils literature, a bit on soil moisture. Typically in my slides, I don't really have paragraphs, but this particular, text was so revealing to me. I couldn't stop, putting all of it in this slide. So I'm going to read a bit. If you look at about almost a century ago, Dr. H.M. Leake stated in the very first volume of the Journal of Agricultural Science that by far the most serious loss is due to the deficiency of moisture of the soil. Thus, the relation of the soil to soil moisture becomes of more than ordinary importance. He further quotes Dr. Polkar of Indian Agriculture. He says that, I quote, "In India, the relationship of soils to moisture acquires a greater significance than almost anywhere else. Such is the importance of soil moisture." Dr. Leake continues that this relationship is fundamental, for on it depends the method for the conservation of soil moisture, for the economical application of irrigation water, and for the treatment of barren and salt lands. And all these problems are direct interest to agriculturists. The problem in all its various branches is enormous, and in a country in which the seasons follow each other with such rapidity. That's what Dr. Singh was referring to, this dynamics of soil moisture. And this variation from one to the other, so marked in a manner, and its frequency happens in such a particular point, if not determined with a period of a few days, must await solutions until the following year. That's kind of a century ago. I was kind of looking at some of the scriptures, and Dr. Gangopadhyay in 1932, looks at some of the Indian literature, old Vedic literature, and he quotes, "No grain, of course, is ever produced without water," right? Water, that's something that we know, and more of water or very less of water, both are very, very bad, and this goes back to Narada Smriti. He further quotes that in the Sabhaparva, which is kind of the chapter 5.5 in Mahabharata, Narada asks the king Yudhishthira if he was attentive to the improvement of agriculture by digging tanks in his kingdom at proper distances, and the key thing is the proper distances. Water should be available in such a sustainable manner that people do not have to depend on rain. The history of water for humankind is very, very old. Many of you guys in the evening prayers probably have heard that this water used to be everywhere, on the surface of the earth, and all the water which is locked in the ice cap, if it melts, are going to be about 3 kilometers. So water is everywhere, right? And if you look at soil, soil sometimes can be in water. I have a small video clip here for you to really watch a little bit carefully. Let's see if you could, Can you see it? Please carefully watch as these tapes are on the ground. You will see these air bubbles, and you can see the earthworm trying to find a place. That's soil. That is soil inside water. I had once doing, I have been doing an experiment once, had a, bhindi crop, lady's finger, and I was trying to really irrigate it with a pipe. And next day morning when I came in, I saw the pipe had leakage, and the dikes had a, standing bottle of water. And what was amazing was that I could see that water coming in, and water coming in up to this here, and there was a pretty much dry zone up here. And so basically water would find its way. Even sometime, you will see that it's not, the soil is dry. So water finds its way, whether soil is under the water, or, or water is inside the soil. It's very amazing that if you look at water, how they really move in the soil systems. If you look at, the history, even Newton would really work on water. Here is a kind of extract from his notebook. This is Newton's notebook. It says that this water goes from A to B, from the soil to the top of the plant, and this means that these juices continually arise up in the roots to the trees upward. We have been interested in water in many different ways, So soil, water, and plant are so intricately related, Here is an experiment I was trying to do, this connection between the water, the plants, the soil, is the roots, Here is, you can see that, two hills of the rice, and I was taking that whole thing out, and I was trying to really see, how the roots are distributed. So, I'll show this. So this is the first one. And then we took that, soil with the hills itself, rice plant, turn upside down, and try to really clean the soil, okay, with a water jet. You could see that there is no roots shown up here, but slowly as you really wash it, the roots become visible, more visible up here, and clean it nicely. You will see a beautiful mat. You see that this, intertwining of the roots of the two plants, and look at that. Both the roots, they really, made nice mat inside this soil. So you could see up. This is how it in nature. This is how it, you take it out and see it. Isn't it amazing how this roots and the plants, try to approach water from soil in a very, very beautiful manner. In fact, water is a remarkable part of the soil plant atmosphere continuum. And this is long recognized from, as long as we know about ourselves. Dr. J.B. Husted in aqueous dielectrics in 1973 wrote, "We can only maintain a really deep interest in what we love. It's not very difficult to become interested in water." And most of you guys who are here, there is one thing common amongst us. Do you know what it is? When we were a small kid, we were holding our parents' hand, the moment we really see a water puddle, all of us would stray away and would really get into that water puddle because we love water, and so it's very, very important that we must know what water is. This is a training program. So what I'll do from here onwards, kind of share with you some of my observation and some of my thoughts about water. Soil moisture. Singh sir already mentioned that there are 30 things that they are involved with. If you look at the very first thing, is it soil moisture or soil water? Look at the definition of moisture. It says that water or other liquid diffused in a small quantity as a vapor within a solid or condensed on a surface. You need to think about, is it water or it's a water vapor? And I will not get into this dichotomy. Whatever it is, the way we describe it is the amount of water which is present in unit volume of soil. You could really express it in the gravimetrics like a mass basis or a volume basis, right? You could really say it as a gram per gram or centimeter cube per centimeter cube. And it's very simple to measure it, right? All you need to do is, take a bunch of soil, put it in an oven and measure the fresh weight, the oven dry weight, and you have a very simple formula to estimate the amount of water which is present in that soil. Well, but the crux of the problem is, if you have different soils, very simple way if you look at it, whether, after 24 hours time, some soil would really reach that, constant weight, or some of the soils, might really reach that constant weight lot long before it, So we need to think, in an era of optimizing our resources, can we really wait for, all those, 24 hours, or can we really develop systems so that we can very quickly measure soil wetness? If you look at what have we done, we looked at neutron scattering, we looked at a mixture of americium and beryllium to, have this fast neutron, which can be slowed down by the hydrogen molecule, hydrogen atoms, and you will be, by taking the ratio of the slow neutrons to the fast neutrons, be able to measure this volumetric water content. But the challenge is that you have a nice standard curve, but if you look at this, it is dependent on the bulk density of the soil, and specifically if you look at the dry soil versus the wet soil, these dependencies are different, right? And so you need to really be careful. Neutron scattering has become almost like obsolete. People have looked at electrical methods, looking at the bulk electrical conductivity of the soil, for example, as a function of the electrical conductivity of dry soil, or electrical conductivity of the soil solution, which is a function of the soil wetness. And this concept is again age old, from the time of Maxwell. People looked at how the suspended solids in a fluid, for example, really be described with the physics. And you could really think about some kind of a current passing through a distance L, and write down the expression for the current, and you will see that the resistance is going to be a function of both the material and the geometry in soil. And people have developed the Wiener array to measure the soil wetness. But the challenge again here is this material dependency takes over. Whether you really have a potassium chloride system or a potassium bromide system, you will see that the standard curves are very different. making the electrical conductivity based methods very difficult. Well, people looked at, frequency and time domain, systems, as Singh sir was again referring to 1980s when we really looked at dielectrics as a method. People noticed that the dielectric constant of the soil is quite texture dependent in low frequencies, and as you increase the frequency from 700 megahertz, means 0.7 gigahertz to 1.4 gigahertz to here something like 10 gigahertz, that textural dependency really disappears. And so basically in a time domain more than 3 gigahertz level, you will be able to look at develop completely an universal calibration relationship between volumetric water content and the dielectric constant. And this is this famous Topps equation, and so lot more efficient, lot more independent method of soil sensing you could really look at using this time domain and the frequency domain approaches. And as again Singh sir was saying, in 1980s, some of the very interesting historical thing took place in University of Kansas. Dr. Ulabi was setting up this studying how the dielectric mixing models can be set up for the soil, and through a series of publications he showed that you could really write simple radiative transfer based simple relationships that can describe the dielectric constant of the soil water mixture, and this really forms the basis of the microwave remote sensing, which is part of this class that you are going to have in next 5 days. So starting from the low frequency L band all the way to C band, these are actually the soil moisture sensitive bands, and you need to really have these mixing models. But one of the, again, if you look at all these models that were developed by Halikainen, Dobson, Dr. Ulabi in their lab in 1985s, they were all in the range of 1.4 gigahertz to 18 gigahertz. And again, if you really mix the smaller frequencies, like somewhere around 0.3 to 1.3, 0.3 to 1.3 gigahertz, the calibration relationships are going to be different. And so, one needs to look at, again, people started looking at how really these mixing models can be really combined, and all these radiative transfer approaches, came up. Fresnel's reflectivity equations being very useful to give you these reflectivities in the horizontal and vertical polarizations, linking the surface temperature of the soil to the reflectivities through this, emissivity to tell you this brightness temperature. And so by measuring the brightness temperature, you will estimate this dielectric constant through these mixing models. And again, I sort of put together this relationship just to really appraise you that these mixing of the microwave, this very basis of this microwave remote sensing lies on that, joining the physics through the radiative transfer and empiricism through the dielectric mixing models, and these kind of basic foundations have been done almost like just about 4 decades ago. So what we are talking about today is, remote sensing, soil moisture sensing is not a very old science, right? And of course, the most recent publication that came out last year, evaluating 6 different kinds of sensing through remote sensing approaches, the satellite products connected with the open loop models, using some 826 soil moisture sensors taken 3 hours, you could see that the correlations are still in the order of about 0.5, and the authors concluded that satellite products alone is not very reliable. You need to really bring in additional models, additional information, so that you can really have a robust estimation, which we really like to have for soil moisture. So the take up here is that poor resolution and environmental hazards making nucleonic gauges obsolete. If you look at electrical conductivity, thermal conductivity based methods are very unreliable. Look at the high frequency time domain methods, they are expensive. You cannot really bring them to the farmer's field. Microwave sensing is really good, but again, accuracies are important. And so when it comes to measurement of soil moisture, we really need to still do a lot of work. We need to really improve how the way we measure soil wetness. Well, if you look at little bit how the soil moisture really behaves, bunch of next few slides I will really put together, for you to show you that soil moisture content is a point data when you measure it. When you look at, its variability, it goes from one location to the other. And here is a set of data that I, as a postdoc, I was collecting. We had this, 6 meter by 21 meter, fields, where we had these TDR probes at 3 different locations, 3 different depths. And there are 5 locations we will take the core samples, okay? And we'll try to really measure continuously the soil moisture, and then we will also, using the TDR, we will also measure the soil moisture in the destructive, like a gravimetric sampling, okay? And what you see here, these solid lines are actually almost like a real-time measurement of soil moisture. And these symbols that you see, these guys are the soil water content in the core samples. And what you see is that, this synoptic sampling would completely miss out the dynamics of the soil moisture that you will see otherwise if you were measuring it in real time. Well, if you look at a larger, spatial area, here is like a big catchment scale, and we had, and this is the elevational differences in the Chilikas, western side in Odisha. We had gone there to really take soil moisture on a single day, and we tried to really put together, their spatial map. You could see that the gravimetric water content varies somewhere from, almost very dry condition to 0.5, and the density that you could see that there's a large spatial variation at a catchment scale. So if you were to really capture by simple gravimetric destructive sampling, then the answer to that question is forget it. You really need some technologies like microwave to capture such a thing, or some kind of digital soil mapping. Well, if you look at, how is the variation of the soil moisture with depth, for example, again, in the same experiment that I was part of it, the surface sample versus the deep, 90 centimeter soil samples, you see that very little variation in soil moisture content as opposed to the response of the sprinkler irrigation in the soil surface. The moisture dynamics are much more, the temporal dynamics are much more in the surface compared to in the deeper layers. Well, if you look at soil moisture content, they are also discontinuous. If you are looking at a, say for example, a layered soil profile, here is, a two-dimensional kind of simulation that I am showing you, a surface top layer, a middle layer, and a bottom layer. So you have a sandy loam in the top soil, a sandy clay loam in the middle layer, a loam soil in the bottom layer, and these are the soil hydraulic properties, right? And if you look at this profile water content as a function of the depth, you could see that from top layer to this middle layer, there is a discontinuity, okay? And so if you are looking at, from a modeling point of view, discontinuous things are not very good. You need to look at continuous thing, and the soil water potentials are a lot more continuous. And so therefore, we need to really move from, kind of the, soil moisture monitoring system to soil water potential monitoring system. Well, that's not, entirely foolproof either. Soil retention curves, if you look at, they are hysteretic. Drying curves and wetting curves are different. And so again, I put together two simulations for a soil with a no hysteretic behavior with a hysteretic behavior. You see, once in the wetting and the drying soil, moisture profiles for the same conditions are completely different. So therefore, again, even if you go for monitoring things in a soil water potential point of view, right, you need to really take into account whether the soils are hysteretic or not, okay? If you look at the soil moisture content, their dependencies on soil properties are very, very high. This is actually the national scale soil legacy data. I show you the distribution of the wilting point moisture content to field capacity for the whole country. So almost like 7,000 data points that I mix and match using the pedotransfer functions, using the actual measurements from the legacy data. You see that the dependency of the field capacity on clay content versus dependency of field capacity with organic carbon content are different. You could see a very strong relationship with the field capacity, very strong relationship with sand content and clay content. And so therefore, understanding this database thing that Sir was saying, that it is very, very important that we really create these soil databases for us to really build this understanding about, whether it's an ecological region scale or whether it's a plot scale. We need to really have these databases for sure. Well, coming back to a little bit about science of the soil moisture, if you ask this question, where does the soil moisture stay? Well, they stay in the soil pores, right? So here is how a agricultural field look like, and for example, if you look at a soil pore, this could look like a big like a wormhole, like a preferential flow path, and this 2-inch diameter sphere, if you put it in a X-ray CT scan, and if you look at a slice of it, this is how the face of that slice looks like. You see that irregular patterns in the soil pore spaces. If you look at the dye tracing of the pore spaces, you see wherever there are this blue color, those are actually the tracing, the capturing the pore spaces. What a heterogeneous distribution of the pore space, Well, if you look at, how does this soil pores and soil pores are really distributed and how they form? It's basically a packaging thing, right? Soil aggregates and will kind of join together. In between there will be gaps, and those gaps are the pore space. And so here, if you look at the size distribution of soil particles, right? So something like a particle size versus cumulative, mass fractions, you will see that, you have some of them are smaller size particle, some of them are medium size particles, some of them are large size particles, right? That's how it is. And bunch of soils, there are 249 soils, if you put together, they would look like this. And almost similarly, if you look at a water retention curve, almost have, similar behavior as the, the pore size distribution and the particle size distribution would be basically similar. And we did a study, where we would look at the, particle diameter and pore diameter and their frequency, and we would look at what is the frequency of the pore size distribution. And what we looked at, that look, the variation of the variance of the particle size distribution, you will see that, under 10% variability, soils are a lot more similar when you look at the pore size distribution. Soils are a lot more similar if the variability is less than 10% with regard to their particle size distribution. So pore size distribution and particle size distribution pretty much really just, kind of follow each other, because they are actually the two sides of the same coin. Okay. And specifically when you really come to the physics of the water, what we really look at, if you have a zigzag, pore size, for us, so we soil physicists, what we have done is have done a lot of simplification, simplification to the tune that we will consider, a zigzag flow path of different size to a cylinder, and the cylinder really filled in a pot of water will have capillary rise, and you could have a capillary rise equation, and you can think of, a soil as a bunch of capillary tubes, and you look at, do a, some editing and sort of combining them together, you have something called this water retention curve. That tells you how a soil would retain water, And those who have taken soil physics classes, and don't worry about these slides, those equations, all that tells you is that change in the water content in time is a function of the change in the flow rate with location. And this is actually the physical relationship that describes the dynamics of water in time and space. And this hydraulic conductivity is another such property that describes the dynamics of water in soil. And of course, you will go ahead, do all these, description of the physics. You need to look at, their water capacity. You need to look at the diffusivity, and I'm going to go very quickly through this. At the end of the day, what you need is bunch of models, right? And describing those soil hydraulic properties, and perhaps if you have, a bunch of these mathematical ways of representing the scenarios in terms of the boundary conditions and initial conditions, you will be able to pretty much simulate how water would change at a particular location as a function of time. For example, here is the simulation of a rice field, a 3-layered system, layer 1, a compacted layer up here, and a porous layer up here. So it's a 4-layered system. And what I have done is I have done simulations here. I have put 5 centimeters of standing water here, and here I put a kind of a sprinkler irrigation, and I would try to show you how this water is going to really show. And you can see here that the water distributions, after 48 hours under these two different conditions, pretty much are different depending on how the soil behaves, and allow it to stay, do the same thing for 240 hours, their behavior almost would look similar, right? Well, so having simulation environment can really allow you to really see how water is going to change. Not only that, it would allow you also, if you know the soil water potential at a particular time, you will be able to do model fitting, So to quickly summarize, what we could really, what we have right now is that the spatial variation of soil wetness in all direction is real, okay? It's dynamic, we understand it. Real-time monitoring, absolutely necessary, right? Science of the soil wetness is very well developed. All we need to know is that have to have our simulation environment. We need to have the soil hydraulic properties. We need to have the speedo transfer functions, the databases that Sarah was talking about, and then we are ready to fly, right? All right, so that's kind of the science of all the soil moisture dynamics. So Debasis, how much more time I have?
You can have, sir, no problem. Now it's at 12 o'clock. You can have another 15-20 minutes or.
Okay. Okay. So you know what? Very quickly, what I have tried to do for some of my younger participants, that try to give you a little bit of flavor about what soil moisture is, how the soil is a very diverse system, where some of our understanding of the soil moisture dynamics is very, very important. And so this means what? We have to really have a bunch of skills with us. We need to understand how it works, and we have to have some kind of tools. We have to have measurement devices, starting from a handheld time domain reflectometer to some kind of a remote sensing data products. And then, of course, after that, we should be able to develop applications that are actually the most important thing. So, what I'm going to do from now for the next few slides, I will quickly go over, over some of my PhD students' work, where we try to really look at concepts to build, applications to build, so that and again, soil moisture is such a diverse topic that, things are already mentioned to us. In my small career, I haven't really worked, on everything, but small thing that I try to work, I will give you some example, so that, have a sort of feel for what all we can do, even if you do not have resources much, and still have a lot of things we could do. All right, so the first one, this is what Dr. Santra was doing. Had a almost very small watershed, 40 square kilometer in the western catchment of Chilika, had 100 soil samples, tried to measure the soil hydraulic properties, basically water retention characteristics and saturated hydraulic conductivity, related those with basic soil properties, and almost almost kind of little bit contemporary to what Singh sir was doing that time, developing the pedo transfer functions for field capacity, and of course, the pedo transfer function for field capacity in our country goes back to 1966 in this classic paper of Abrol sir, where the surface area is related to the field capacity, and so a lot of good work done in the by our Indian scientists. So we were looking at if we can really measure the parameters of the water retention, Hand-Newton water retention curve from the basic soil properties, and so we are building this parametric pedo transfer functions, and Priyavrata went ahead, tried to develop this spectro transfer function using the setup that Dr. Sahu, Ravi is there. Dr. Sahu was, measuring those, spectral reflectance, and we had a perfect collaboration. We really built these, the very first method to estimate soil hydraulic properties, parameters actually, of soil water retention curve from the spectroscopic data. We should have, standing now, I think that Ravi, me, and Priyavrata, we should have really patented this particular thing. But nevertheless, what Priyavrata did, he went down to really create this regression kriging maps for the soil hydraulic properties for the watershed, and tried to build this classification of the soil based on, this soil fuzzy classification of the hydraulic properties, a method of upscaling. And again, Singsar was referring to that, from point measurement, how could you really get to the larger scale, So we were combining this numerics, the kriging approach to, part of the remote sensing data, and create these maps of the soil hydraulic properties. So build hydrologic response unit, based on actual hydraulic characteristics, not based on the soil properties. So that was a very, very unique work that Priyavrata was trying to do in our lab, and that helped us to describe the performance of the hydrologic models in a better way. Then again, I see that Mukund is here. One of my another PhD student was looking at, why the rice fields are water guzzlers. Why we need 300 centimeters of water for growing rice in one season? That's not really good enough. And Mukund would really go ahead and do bunch of measurements, create this, water, preferential flow paths, and he noticed that much of the water actually, passes through the soil under these bunds that we lay out in the rice field. And we, that's me about 15 years ago. So we looked at a complete cross section from one side of the field to the other side of the field, went down there and measured at every location the bulk density measurement samples, and created a two-dimensional map of soil bulk density. And guess what? We looked and we found that wherever the puddling is done, the soil is compact. Underneath these bands, the soil is a lot more porous. Of course, water is going to, once you really have the standing water, water is going to do this bypass flow through and then get lost wherever this find a path. And therefore, a lot of water will be lost just because you have a lot of, big, large, preferential flow paths. Well, this picture that I am showing to you, this was in my own farm, in my own village. In the month of May, I was trying to dig a pit, and I noticed that in month of May, look at this crab sitting at a depth of about 1 meter, cooling, hibernating himself, getting ready that monsoon comes in, he will again come back up and make these big holes in the rice fields. And so therefore, what we try to do is that these large flow rates in the underburned soils versus the in the infield soils because of the puddling, can it be really taken care by simply doing some kind of a disturbance of the burn? And guess what we did? We tried to reduce this hydraulic conductivity of the burn substantially by plugging the burns, and that really gave us a water saving of almost 80 centimeters of water. So almost conjunctive use of water you could really use for growing rice if you really stop the lateral flow and seepage or the preferential flow paths. We really went for a step forward. We said, look, can we really do another set of experiment where we will reduce the water uptake. So we looked at this recoverable water stress. So what we try to do is that we went down there, we said, look, we are going to use all kinds of measurement. We will put these tensiometers, we will have these CDR probes, and what we will do is, create this water stress in the rice fields, and so basically we applied water stress of about 14 days of, no watering, and so that the soil water potential shoots up to almost 100 kilopascal, about say 1 bar, and try to look at, whether, it is possible to still maintain the same yield. To much of our surprise, we notice that as long as the water stress is restricted to this active tillering stage, you really get a very nice yield compared to your control where there is no water stress. That really showed us that, look, if you really increase the soil drying, that means you apply water stress, you might really get a yield advantage. So but of course it has to be a recovery. It has to be a recoverable stress. You should not really stress the plants to the point that it is not going to be able to come back up. Okay. So again, engaging with science, engaging with the measurement, engaging with, understanding about the system, engaging with the simulation environment, we showed that it is possible to really work with the stressed plants, impose stress in a very controlled manner, still get the same yield. So saving water is possible. Of course, if you really go out and do bunch of measurements. A step forward we took, we said, look, is it possible for us that, because the tensiometers are not always working, is it possible for us, we could really monitor the soil wetness or the soil water potential using a spectrodiometers, the optical and thermal data that Sir was talking about. Can we really look at plant as a proxy to know, the soil wetness regime, soil water potential? And so we did a bunch of experiments, and we noticed that you could really, monitor the soil water potential nicely with the tensiometer, but those tensiometric data, you could really measure along with this stress parameter, like leaf area index, like the canopy water content. You could measure it using spectroscopically, vis-a-vis, you will be also able to measure the soil water potentials using the spectroscopic data. And we noticed that specific wavelengths like 2012 nanometer could be a very important critical parameter for, measuring water stress. So a thermal part of the electromagnetic spectrum. Okay, so kind of to recap, that understanding of soil and moisture obviously leads to a lot of solutions. So through my students' work, what we observe that soil hydraulic properties can be used to improve the hydrologic models. Water use efficiency can be really improved. And you could really go to high-end technologies like this DRS or the reflectance spectroscopy to look at, how, you can have a better control on the soil moisture. I think that the key learning out of these, to me, if you ask me, is very simple, that we need a lot of measurement, lot of modeling, and they are actually critical steps in managing water in our agricultural systems. And most important thing that Sir was pointing out, that systems approach, not just, measurement and isolated location or in a narrow window of time. We really need to look at things in totality. We need to really look at things in an inclusive manner, look at as a system approach. And that's what is needed to use and as well as preserve, you know, using water, we are doing it very well. There is no doubt in that. You know, we haven't failed in using water. But what we are failing, you know, if you look at the drought scenario maps, the Niti Aayog put together a couple of years ago, you know, what we are kind of doing is we have a serious question mark whether we are preserving this very unique gift of nature that is synonymous with us. Okay, so yesterday, you know, late night, Debasis told me that, can you really tell something about the future of soil physics and hydrology? You know, I think that, you know, whatever Sir just said, those 30 points, you know, from agro advisory system to, you know, database of basic properties through, you know, dynamics of soil moisture, upscaling, wireless sensor network, all of that are very, very important. And you know what? It's very, very important that we recognize that it's very, very important that we recognize that we used to be in the forefront and we are on the forefront. You know, this, I don't know if some of you guys can recognize this text. This is a quiz for my participants. Do you know where this text comes from? This text comes from 1948 paper of Dr. Penman. And as he was developing the famous Penman equation, you know, utilizing the data set collected at the Indian Agriculture Research Institute, the then Pusha, you know, using all these rainfall, energy balance, you know, drainage data from 1907 to 1934. And you know what? It's interesting that he writes, by the courtesy of the Indian authorities, the rainfall and the drainage data was given to him, you know, almost a decade ago, right? A decade ago, we used to share our information, and something that gave rise to this beautiful, you know, science, the energy balance and the evapotranspiration, you know, estimation. So this is actually my last slide, to be able to tell something like a roadmap in front of, you know, Dr. A.K. Singh is not my cup of tea, you know, but all I will tell that, you know, we should still probably have an introspection that Narada saying Yudhishthira are large tanks and lakes constructed all over thy kingdom, O great king. And I think the key thing is at proper distances, right? Because at proper distances is important, because if you are looking at like a sustainable manner, you know, in a very precise manner, everybody should have access to that good quality water, right? And so I think that we need to really do that. We need to have our data open. We need to have our every station data on weather open. Okay, that's only the way we can really build new things. And I think that's the road forward that we should look for. I'm going to stop with this and, you know, have some you know, questions if you have. But thank you again for having me for this talk. I don't know if I've kind of tried to give you an overview of soil moisture or not. Thank you so much.